How's it going, everyone? Alright, I hope everyone did alright on the test. I hope to have it graded by next Monday. We'll see how that goes. Anyway. Do you have any questions before we begin? I mean, you don't have to on the multiple choice, especially if you got them right, because I think you'll know after you submit the test whether you got them right or not. But if you didn't get them right, you definitely want to submit your work just so you can show that we can get some partial credit from that. You know. Our next test, I would anticipate about 3 weeks. Give or take a day or two. Yeah. Okay. Once I get all the tests graded, I'll spend a little time going over the exam. Probably Monday, like I said, and I'll ask if there's any questions and so on. Okay, today we're going to start chapter 3. Chapter 3 is on functions, and we'll be looking at some different things as well. But mainly functions. We're going to look at some graphing in this chapter. Things like that. So section 3.1, we're going to start with functions. Okay, now when we talk about a function, takes an x value and returns a single y value. as a result. So we'll never have more than one y value paired with any x value. So for our notation, for example, we might see f parentheses x, which is f of x, is equal to 2x squared minus 3x plus 1. Okay. And so if we wanted to evaluate f of x at x equals 2, for instance, then we would plug in 2 for x, and that means everywhere we have an x, we replace it with 2. So f of 2 is 2 times 2 squared minus 3 times 2 plus 1. No, we'll get through chapter 6, which is, the limit as far as how far it to go. We might cover a little bit out of chapter, I think it's 7 or 8, like 1 or 2 sections, but that's it. Thank you, Natalie, and I'll go ahead and, if he does continue with trouble, and he can certainly watch the recording, and just have him let me know when he does so I can count him present. So now, one thing we have to be careful of when we plug in values into functions like this is order of operations. And again, the question is, do we do our multiplication first or we do the exponent first? Well, we know order of operations, exponent is always first. So we would do the 2 squared, which is 4. And then we would go through and do our multiplication, which is 8 minus 6 plus 1. So it'd be 2 plus 1 is 3. So f of 2 is equal to 3. And this would correspond to the point 2, 3 on the graph of f of x. Alright, so evaluating a function, pretty straightforward. The main thing, like I said, is following the order of operations and making sure that we get our value calculated correctly. The other thing here is that we plugged in a value for x, and the result here is then a value for y. So 3 would be considered a y value. And so it corresponds to the point 2, 3. That would be our ordered pair that is 1 point on the graph of f of x. That's something we'll explore further, I believe, in the next couple of sections, 2 and 3. I forget which one. Okay. Now, one of the main things we want to talk about in this particular section is finding the domain of a function. Okay, awesome, William. So when we talk about domain, this is the list of all x values for which a function is defined. Well, I should say for which a function is real and defined. Now, when we say a function has a real value, that means that none of the values that we get are imaginary. And the way that we arrive at an imaginary number is if we take the square root of a negative. So when we say real, that means we're excluding imaginary numbers. We're excluding square roots of negatives. So real excludes imaginary numbers, which we know are defined as square roots of negatives. And when we say a function is defined, that means quite literally it's not undefined, which is not great English from a traditional standpoint. I think I need parentheses there. But when we say something is not undefined, it means we don't divide by zero. Because when we talk about what makes a value undefined, it's that division by zero that makes that happen. And so essentially we define a domain based on what terms need to be removed from the domain, which is anything that results in an imaginary outcome or anything that results in an undefined outcome. If the result is not imaginary or undefined, then we can say that that particular x value that was plugged in is part of the domain. Okay. So there's three types of functions that we want to discuss in this particular chapter and throughout the next couple of chapters, actually. These will be the main types of functions we'll be working with. And that is polynomial functions, rational functions, and radical functions. Okay. Now, polynomial function is similar to the quadratic equations and quadratic functions we've been working with so far, largely. Rational function basically means a ratio of terms, which means we have something divided by something else, and usually means it's a variable that's in the denominator. And finally, radical functions means there's a square root there, square root of a variable. Now, if the division by a number doesn't make something rational and square root of a number doesn't make something radical, is when the variables are involved in that it makes it rational or radical. So, for a polynomial, first of all, Polynomials are defined as combinations of variables raised to whole number powers. Okay. And as an example, we would say, f of x equals, say, x to the third minus 3x squared plus 7x plus 1. Everything there has a whole number exponent. Whole number means it's a positive integer. So 1, 2, and 3 certainly qualify. X to the first, x to the second, x to the third. And technically the constant is x to the 0, which still qualifies as a whole number. Because the whole numbers start at 0 and count upwards from there. And so that's the kind of thing, that's how a polynomial looks like. Now, when we talked about the domain of a function, we said that we want the list of all x values for which a function is real and defined. And again, we base the domain on what is being excluded from the domain, largely. Because we don't want it to be imaginary, and we don't want it to be undefined when we plug in a value for x. Now, what causes an imaginary number is where we take the square root, and what causes an undefined number is where we divide by 0. If we look at a polynomial, there's nothing here to divide, so we'll never divide by 0, and there's no roots in this equation, no square roots. So we'll never have to worry about taking the square root of a negative number. Because of that, there's really no restrictions on the domain. So domain says that x can be any real number from negative infinity to infinity. Okay. Now, as far as our notation goes, we could say negative infinity, comma, infinity. This is our interval notation. Generally, this is what we'll use for a lot of things, but not necessarily everything. Or we have the option in this case of saying, in this symbol, the R with the extra line in front of it, this would be considered all real numbers. Which is another way of saying from negative infinity to infinity. So in that case, basically there's no restriction on the domain, and this is actually true for all polynomials. All polynomials have an unlimited domain, so it's anything from negative infinity to infinity. Okay. You know what? I don't have a word for that symbol. I just call it all real numbers, because that's what it stands for. Basically a fancy R with just an extra line in front of it or through it. Generally we draw both lines and then close it up partially from there. Okay, polynomials are generally the easiest ones, and we don't really worry about them too much as far as domain goes. But it's nice that everything's the same, at least for polynomials. Unfortunately, this is not going to be true for irrational or radical functions because those are going to be very case specific what the domains are going to be. Okay, so let's talk about those next. So next we'll look at rational numbers. Now, rational numbers is this type of, or not numbers, sorry, functions, which includes rational numbers, but not, there's more to it. Okay. So a rational function is any function that's a ratio of two variable expressions. As an example, we could say f of x equals 2x plus 1 over x squared minus 6x minus 16. This is a rational function because we have x's both on the top and on the bottom. Technically speaking, we only need x's to be in the denominator. We may just have like a constant on top, but generally we see variables in both parts of this fraction. So rational functions are fractions, basically, that involve variables. Alright, now we go back to what we talked about domain. We said that for a value of x, if x was not in the denominator, it would actually be a polynomial. Because that means it would just have just a number on the bottom, and that number would just be, if we just divided it into each term on top, we'd make it a polynomial. So if we had 4x squared plus 2x plus 8 over just a 2, we would divide that 2 into each number. 2x squared plus x plus 4, that'd just be a polynomial. Even if those were fractional numbers, as long as x is raised to a whole number, that's what makes it a polynomial. So. We'll get to inverses at some point. I don't remember if it's this chapter. I think it's chapter 6 we get to inverses. Beginning of chapter 6, because when we start looking at logarithms and exponential functions in chapter 6, it's useful to understand inverses to help work with those. Okay. Yeah, so we need to have an x on the denominator at least, even if it's not necessarily on the numerator. Now the domain, again, we're not going to be taking any square roots in this equation, because there aren't any square roots present, so we don't have to worry about numbers being imaginary if we plug in a value for x. What we do have to be worried about is possibly dividing by 0, because we do have division present in the equation. Okay. So for the domain of irrational functions, the domain is all real numbers except the values of x that make the denominator 0. Okay, because if the denominator has a value of 0, then we're dividing by 0, and this would be a numerator divided by 0, which makes it undefined. Okay. So the solution is, if we're trying to find the domain of a function, such as this one right here, we would take whatever's on the denominator, set it equal to 0, and solve for x. So our approach is to set the denominator equal to 0, and then solve for x. Okay. So if we took x squared minus 6x minus 16 equal to 0, this is a factorable trinomial. We need two numbers that multiply to negative 16 and add to negative 6. Negative 8 and 2, good. So x minus 8, x plus 2 equals 0. And so we get x equals 8 and x equals negative 2. Now again, when we state our domain, we're not saying that 8 and negative 2 are part of the domain. What we're actually saying is the domain is all real numbers except the 8 and the negative 2 that we found that make the denominator 0. Okay. Now the other way that we could write that is just x is not equal to 8 or negative 2. And that's generally a more concise way of expressing that answer. Okay. If this ends up being like a multiple choice question, that's probably how I'll express the answer in the multiple choices, with the not equals sign. Okay. So that is rational functions. Again, for rational functions, we set the denominator equal to 0, and then solve for x. Like we did, we took the denominator of our function here, our rational function, took the denominator x squared minus 6x minus 16, set equal to 0, factor it in this case, which most of these problems will find that rather than wasting time with the quadratic formula, they'll just get something factorable to us, which is nice. Then we factor it and get our two answers, and their domain is everything except those two answers that we found. Or again, we could just say x is not equal to the 8 or the negative 2. Now, radical functions, these are functions that contain a square root or contain a root. whether it's a square root or a cube root or etc. That's what we're referring to. Now, for functions with odd roots, there's no restriction on the domain. And when we say there's no restriction on the domain, we mean the domain is negative infinity to infinity. Okay. That's only if the root is odd. That means that if we have a cube root, for instance, we could plug in any positive x or any negative x and still arrive at an answer, a real answer. But for even roots, if we have a square root, for instance, we have to be concerned about the possibility of imaginary numbers. So it's possible to get an imaginary answer and we want to leave those imaginary answers, or leave the values of x that give us the imaginary answers, leave those out from the domain. So we restrict the domain accordingly. Okay. Now, the way that we actually do this is, this one will be easier than the rationals, is that whatever expression is under the square root, that we want to make sure that expression is at least 0 or larger. Okay. So the expression under the root is greater than or equal to 0. So now we just have to solve an inequality in order to determine the domain for an even root function. Okay. For example, we have the function f of x equals 3 plus the square root of 6 minus 2x. Now, first thing we want to look at here is we're only looking at the expression that's under the radical. Just even roots, sorry. In fact, if we look at the textbook, the only thing they ask us is even roots. The odd roots they leave out because they know there's no, I mean, the domain's just negative infinity to infinity. There's really nothing to ask there. I like to mention it for completeness sake. So we have some extra terms here, like this extra 3 plus in front. We want to make sure we ignore that. We're only looking at what's under the root, which is the 6 minus 2x. And in order to find the domain, we need 6 minus 2x to be greater than or equal to 0. So the question is then, how do we solve for x? Well, this is just a linear inequality. So we solve for x the same way we solve a linear equation for x, which is to get x by itself on the left-hand side. Now with an inequality, we especially want to make sure x is on the left-hand side and not the right. Otherwise, it makes it a little more difficult to read. So I would say, let's move our 6 over. And if we divide by -2 on both sides, what would be the result? Three. What about in between? Is it still greater than or equal to? So we divided by a negative number in an inequality. So that is the one thing that's different about working with inequalities than working with just normal equations. If we divide or multiply by a negative number in an inequality, it actually changes the direction of the inequality. So it would make it a less than or equal to. That's the other thing I wanted to mention here, since we are solving inequalities, essentially. We know that we start off with this greater than or equal to 0, but if the x happens to be negative, which it is here, ultimately we're going to end up with a less than or equal to whatever the number is here. Notice how this works. If we plug in 3 back into this expression, 6 minus 2 times 3, 6 minus 6 is 0. And square root of 0 is 0, so 3 is valid. And this says we should be able to pick any number less than or equal to 3 and we'll be okay. For instance, if we pick 2, 6 minus 2 times 2, 6 minus 4 is 2, square root of 2 is a real number. It's irrational, but it's a real number. If we plug in 1, we get 6 minus 2 times 1. 6 minus 2 is 4, and the square root of 4 is just 2. Okay. But if we plug in anything larger than 3, like 4, for instance, 6 minus 2 times 4 is 6 minus 8, which is -2, and the square root of -2 is imaginary. And that's the imaginary case that we want to leave out of this. We don't want our domain to include imaginary numbers. We just want real numbers in our domain. We did some talking about imaginary numbers back in chapter 1, but really we won't be worrying about them for probably the rest of the semester at this point. We want to instead focus on real numbers, especially when we're talking about domains. We want to make sure we're only working with real numbers. So our domain is just x being less than or equal to 3, or with interval notation we could say -infinity to 3. And because it says equal to, we'll put a bracket there. Do we ever put a bracket if we have negative or positive infinity? Or do we always use parentheses? Well, when we put a bracket there, it means we're including that number. So this means we want everything up to 3 and including 3. A parentheses would say everything up to 3, but not including 3 itself. That's the difference. Right, so it would be not equal to. So the idea here is that we get everything up to negative infinity, but not including negative infinity. Well, the reason we never include infinity, whether it's positive or negative, is because infinity is not an actual number, it's more of a concept. We know that the numbers just keep going, but there's no one number we can say is larger or smaller than anything else. Okay? So if we think we have the smallest number ever, we can divide it by 2 and make it smaller. And if we think we have the largest number ever, we can add 1 and make it larger. You know, it just continues. And so technically we never reach infinity, so there's no way that we could actually include it in our domain here. So always parentheses on infinity, but with actual finite numbers like 3, we do have to pay attention to, if it's equals to, we'll include the bracket. If it's just less than or just greater than, we'll just put our parentheses there. Okay. Now again, the larger concern is still finding the domain of a radical function here, which is to say, whatever is under the radical must be greater than or equal to 0. And then we just go from there and figure out the domain. Okay. The next thing we want to look at in this section that's correct, August. So we're saying everything from negative infinity to 3. Mm-hmm. When we use that interval notation, basically we're saying here's the starting value and here's the ending value, and we get everything in between. So if we say a comma b with parentheses on a and bracket on b, that's saying a is less than x is less than or equal to b. So x is everything in between, but also including b itself, but not a. If we say bracket a comma b parentheses, then that would be a less than or equal to x less than b. So this time it's everything between the two numbers, but also including a and excluding b. And if it actually includes infinity, like we might have, from 2 to infinity, we would just say x is greater than or equal to 2, and it's assumed that it goes to infinity from there. So probably more of you are, I imagine a lot of you are familiar with interval notation already, but we want to make sure we get the details down correct. And again, you could write your answers in inequality notation like we have here on the right. So either one is fine, but generally we would prefer this method. So. Right, and what really makes it difficult is that when you say 3 comma 4 as an interval, where we mean 3 less than x less than 4. So it looks like an ordered pair, absolutely. So we have to be mindful of what context our answer is going to be describing. Like, are we solving for an ordered pair in this problem, or are we solving for a domain? that tells us what this answer actually means. Yeah, I mean, we could put it on a number line for sure. The whole point is we want to work around the graph by expressing it with this notation. So certainly the interval notation is more concise than the inequality notation. There's another notation here since we're talking about it. If we use braces instead of parentheses or brackets, this just means x equals 2 and x equals 3. So whenever we have the braces, we're just listing the outcomes, which is 2 and 3 specifically. There's nothing in between in that case, just the two numbers themselves. Exactly, August. By the way the question is posed, we'll know what the answer is supposed to signify, whether we're talking about an ordered pair or we're talking about an interval. Yeah, it's part of, just learning the context clues and just being comfortable in general with math. Okay. Mm-hmm. So the next thing we look at in this section is what's called the difference quotient. And the difference quotient is a measure of the rate of change of a function. Specifically, we could call it the average rate of change. That might be better. It's certainly more accurate. But the way that which way to utilize it in later courses is to establish just the rate of change itself. Actually, in calculus, we'll use the difference quotient to indicate an instantaneous rate of change. Like, how quickly is the variable changing at this moment that we're interested in. Let me write down average rate of change. Unfortunately, we don't have a lot of context where we can use the difference quotient just yet. Like I said, it's actually a fairly significant formula for calculus. So for those of you that plan to go on to calculus, you will certainly see this formula again. The good news for those of you that go on to calculus is once we learn this formula and work with it a little bit, we immediately figure out how to go around this formula and skip it entirely. But that's a discussion for another course. And then it's also so typical of math where we learn how to do something the hard way, and then after we get that sorted out, we then learn the easy way. Anyway, so the difference quotient, which I'll abbreviate to dq appropriately, is f of x plus h in parentheses minus f of x and divided by h. Now h is whatever value we want to be, although eventually it's going to be a specific number in calculus, but for now we can just use h as h. We don't really have to worry about the value of h, it turns out. What we are concerned with are how does the function interact with being plugged into this difference quotient, and that will actually tell us the average rate of change formula. So, just to kind of illustrate what this function or what this difference quotient is doing, suppose we have a value for x here, so this is f of x, this coordinate. Actually, f of x is the y value. And then we have a second variable over here, which is x plus h. Now, that means the distance in between is h. So the distance from x to x plus h is h. Okay, so h could be anything. Yeah. And so what we're actually measuring is the average rate of change from here to here. But more specifically, the difference quotient is the slope of the line connecting the 2 points. Okay. So if we connect these 2 points together, then the difference quotient is actually measuring the slope of the line connecting the 2 points. So if it's f of x plus h is higher, then we have a positive change, and if this point was lower, then we have a negative change. As we know, a positive slope is sloping upwards from left to right, and negative slope would slope downwards from left to right. So this is way more than we really need to understand for what we're doing in this section, but I'd like to give it context for those of you that do plan to move forward with mathematics in general. So, well, specifically on calculus track. So yeah, we can define the difference quotient as the slope of the line that connects the 2 points. Okay. But really, the difference quotient is just a formula that we have to plug a function into. Generally, the hardest part is that f of x plus h term, and that's the one that gives most people fits. So. Okay, for instance, if f of x is 2x plus 7, so if we have f of x is 2x plus 7, and we want to find f of 2x plus of x plus h, sorry, that means wherever x is, we replace it with x plus h. So x appears in one location, so we replace x with x plus h. Okay. And that's really all it is. It's just a substitution. Just replace the x variable by itself with the binomial term x plus h. And what I would recommend is we put it in parentheses to make sure that the correct order of operations happens around it. For instance, because we have 2 times this term, we're going to have to distribute the 2 to both of those terms. So there'll be 2x plus 2h plus 7. Okay. if we have f of x is x squared plus 3x minus 5, and we want to find f of x plus h. Okay. This time x appears in two different places, so both of these x's need to be replaced with x plus h. So again, replace x with the binomial x plus h. Okay. And then we simplify according to the order of operations. For whatever reason, this is one of the most complicated concepts we have in college algebra right here. And in my students, usually from past students, usually they either get it or they don't, which is unfortunate. But this one's really just two options. They get it or they don't get it. And hopefully all of us will get it, and it'll be okay. But you know, if you're not going towards calculus, this is just, it's not anything that's going to affect you. So if you don't quite get it, that's fine. We'll have to do the test still, so you would probably prefer to do well on that. But you know. Anyway, this one we still need to simplify, and this one's a little bit more challenging to simplify because we have the x plus h squared term. So what I would recommend, some of you may be more or less confident in doing this, is we could write it as x plus h times x plus h. That way we know that we have to FOIL those together. Some of you may already be comfortable with squaring a binomial, so that's not a big deal. But in case we're not sure, I definitely recommend writing it as a product of two binomials, so we can follow the FOIL operations. So what is x plus h times x plus h once we multiply all that out? Does anyone have that? We FOIL these together. Good, good. X squared, 2hx, h squared. Right? Now we could write this as 2hx or 2xh. The order is not important. I generally write 2hx, one because it's alphabetical and it looks better to me that way. That's me personally. The other is that x is our main variable, and then h is generally considered a stand-in for a constant, and so 2hx would be any order is fine, because you can write 2xh, and that's perfectly fine also. Anyway, and we still have the rest of the term here, 3x plus 3h, and then minus 5. Now, we look at that, And we notice that there aren't any like terms here. So that's actually our whole expression right there. Now this is certainly the biggest barrier to being successful in this type of problem, is correctly finding the expression for f of x plus h. That's why I wanted to kind of highlight the two different cases here. One where we have a linear equation and one where we have a quadratic equation. Generally on our tests, both our chapter exam and the final exam, we like to have a quadratic equation and then have you find the difference quotient for that. Okay. Now, let's carry the problems further. Let's find the difference quotient for f of x equals 2x plus 7. Well, we said f of x plus h already was 2x plus 2h plus 7. And our difference quotient formula is f of x plus h minus f of x divided by h. So that means in the numerator, we'll plug in f of x plus h first. So it's 2x plus 2h plus 7. From that, we'll subtract f of x, 2x plus 7, and divide by h. Now, notice that I put both terms in parentheses with a subtraction in between. I always do that just to make sure we remember that the minus does have to be distributed. We don't technically need parentheses around the first term, f of x plus h. But I think it's a nice way to visually separate them so we can see where each part is being plugged in. Anyway, what can we simplify the numerator to? Yeah, you jumped a little bit ahead, that's fine. 2x minus 2x, that cancels out. 7 minus 7, that cancels out. So we still are left with the 2h on top, and we have h on bottom. So we simplify the numerator to 2h. Our denominator is h, so now we can just cancel that and say our result is 2. So that means the average rate of change for this function is 2, which is actually identical to its slope. Because it is a line, any distance or any slope that we find between 2 points on the line is going to be the slope of the line itself. So in that regard, the difference quotient for f of x equals 2x plus h generally pretty, like any linear equation is generally straightforward. Yeah, so we end up with 2h divided by h, which gives us to 2. It's a little bit more challenging for the quadratic formula, x squared plus 3x minus 5 that we looked at before. So above, we already found f of x plus h. We said that was x squared plus 2hx plus h squared plus 3x plus 3h minus 5. Okay. So for our difference quotient, take all of this first, all of f of x plus h first. Minus 5. Subtract, and then we put in f of x, which is just the function that we started with. And the whole thing is divided by h. Okay. Now what terms can we cancel in the numerator this time? Cancel the x squared because we have x squared minus x squared. 3x minus 3x, those will cancel. And negative 5 minus a negative 5, so negative 5 plus 5, that cancels as well. Now, what we notice happens, and this is actually true for every polynomial that we use, is the original polynomial here, f of x, all three of those, or all of those terms, however many they are, should cancel out with terms from this expression. Okay. So x squared, 3x, and minus 5 should cancel out with x squared plus 3x minus 5, because that's being subtracted. So by subtracting itself, it cancels out. Now, we look at what's left over. We have 2hx plus h squared plus 3h. I really would prefer to keep it on this page. 2hx plus h squared plus 3h over h. And then we divide everything by h. What happens after we divide everything on top by h from the bottom? Two x plus h plus 3. And so that would be our difference quotient. Yeah, so the h divides into each of these terms. So h is like the common denominator here. So 2hx over h is just 2x. H squared divided by h is a single h left over. And then 3h divided by h is just the 3. Exactly. Okay. Any questions on that? By no means the easiest thing that we do. But if you can get that, then we know for sure there's at least one problem on the next test and on the final that we'll be okay with. And I can tell you right now, it's going to be a quadratic rather than a linear equation. So this is a very good example for what we might see. Right. For homework, we're going to be on page 216. Let's look at numbers 'Oh, there we go. We'll start with 51. 54. 55. 'Then also 59 and 63. Those problems are all on domain. Next, the difference quotient problems. Look at 83. 85 and 87. Also, if you would look at 109. It's a word problem, but all they really have you do in that problem is plug in values. Now, what changes is whether we plug in the value for the x variable or whether we plug in the value for the function value. That's something to pay attention to. And if you do have any questions on that, we'll just go over that first next time. So. Alright, so just look at those for now, and we'll continue on to section 2 next time, and hopefully I'll have your grades for you also. I expect to, but I can't guarantee it, unfortunately, but I do hope I'll have it done. So. Alright, you all have a good rest of the day, and a good weekend too. I'll talk to you all on Monday. Bye. Right, 83, 87, or 83 through 87. Yeah, that's all difference quotient.